Hello everyone, welcome back. So let me just share my screen. So yesterday we sort of were in the middle of proving the Res Representation Theorem for C01. So I'll pick it up from where we left, the proof. So if you recall, this was the statement. So delta is a positive linear functional, and we wanted to represent it as a integral, right? And we've gone halfway into the proof already. Right, so we were here. What had we done? We had actually constructed, so we started with this delta and we had gone to the bigger space, C01, we recognized as sitting inside B01, which is also a norm space. And then I applied the Hahn-Banach theorem to find an extension delta tilde of delta. And here I did not write this, but the norms are preserved. And also during the course of showing that a positive linear functional on C01 is bounded, which we did at the beginning of the proof, we showed this. Okay, so this is new. It's not new, but I didn't record it separately. Okay, so that is how we got a linear functional on B01. And using that, I constructed these functions alpha. Okay, so what was alpha at x? It was delta tilde of the characteristic function of the interval 0x, right? And when we did this, then we showed that alpha is actually monotone. And to do that, we needed this property here, that the extension is positive. Okay, so this will be a exercise for you in the tutorial. I will show that this extension, the extended linear functional, is also positive. Okay, so once we have done this, you have that alpha is monotone. Okay, so now we have this function alpha in hand. Guys, are you with me? Are you able to hear me?
Yes, ma'am.
Yeah. So you recall all of this, right? So after that, what I did was I introduced these quantities. Remember, the idea is to get to that Riemann-Stieltjes sum sort of, in a way. Okay, so now this is beginning to look a bit like that, not exactly. And now you note that f is uniformly continuous on 0, 1, because it's continuous on 0, 1, so therefore uniformly continuous. And I make this claim. Okay, please note that Fn need not be, is in fact not in C01. So, but we also have the larger space B01, bounded functions on 0, 1 with the same infinity norm. Okay, so now we are saying that Fn should converge to F as n goes to infinity. Can you see why? Is it easy to see? So you have to use the uniform continuity here of F. Okay, so maybe I write this. So let's start with the usual, try and prove it by the usual silent method. So I just apply the uniform continuity of F to get hold of a delta. Of course, TS have to stay in our interval. Right? Now you pick up any T. So you can find, so remember what were the J by N points? They were, so this is the partition with this is what we have done. This is 2, sorry. So this is a typical partition Pn of 0, 1 we have taken. So T must fall one here somewhere. So T say belongs to, sorry, just 1 minute. Okay, I have a small problem. For some reason, give me a minute. Just can you stop the recording for a minute? I need to fix. I'm not able to write anymore on this. Can you hear me?
Yes, ma'am, we can hear you, but
My
we can't
screen
see any. Yeah, screen is stuck.
My screen is everything is stuck for a minute. Just give me a second. I'm going to stop sharing and see what's happening.
Is there a problem?
Disconnected हो गया.
Number, sir?
Sorry, Sachi was not able to write. She may have disconnected to fix something on her computer.
Okay.
So she asked for the recording to be paused for that. Can we pause it?
Can you see my writing appear?
Yes, ma'am. We can start.
Okay.
Yes.
So T will be in one of the J knots or T is 1, right? So you can see what would FNT minus FT be? It will be, if T is 1, what do you think you'll get? You'll simply get 0. See, here is Fn here. Yeah. So you'll be 0 if T is 1, and otherwise you'll simply get F J naught by N minus Ft. Okay. So this means is less than epsilon for all n. If I choose, now I want to use this thing here. If you can see top of page 13, where the uniform continuity I had written in terms of epsilon and delta. So as long as I choose n to be greater than than equal to some n naught, where I will choose n naught appropriately. Yeah. So this means, so this was any t, I picked up any t, and I have mod of this is less than psilon. Okay. And therefore, sup. So please note here what is important is this n naught does not depend on the choice of t. Okay. The sup okay, so this establishes our claim. This is infinity norm, of course. So therefore, Fn converges to F. Fine. Now, so, and this is all happening in the space B0, 1, infinity. Because though F is a continuous function, Fn needn't be, right? But we have seen this delta tilde is a bounded linear functional. So this implies, so this must go to, fine. So that means and remembering that this delta tilde is just the extension of the original delta that we started with, and F is continuous. So F is in, you have this. Okay. So now let's identify what these quantities are. Go back here. So delta Fn's are these. So when I apply this linear functional delta tilde to Fn, now this Fj by n is just a scalar. And because of linearity of delta tilde, you will have delta tilde applied to chi 0 j by n minus delta tilde applied to chi of 0 j minus 1 by n. Okay. But we had given a special name to delta tilde is applied to chi of these intervals. What was that name? We defined alpha to be this. Okay. So coming back, since Fn is just so I'm using linearity of delta tilde and then just the definition of alpha. And that is simply okay. So now this looks like the Riemann Stieltjes sum I was talking about the beginning of last lecture. So what will this limit be? Anybody? This was that thing I had defined right in the beginning with respect to alpha now. So what did we call it? F I think this is the notation. Maybe the order might be slightly different. Okay, and this we denote simply by and from 1 and 2 now, we are able to realize this linear function started with as an integral. We represent it as an integral, at least for all the functions which are in C01. Okay, so that brings us to the end of this theorem, which is just the Res representation for C01. Okay, go back to the statement again. What are we saying? Oops. So you have a linear functional on C01 to R, and you can realize it as an integral. So the next question to ask, and this is the original proof, not the proof, but the original statement of Res theorem in early 1900s. So the next question to ask is, what if we replace this nice closed bounded interval 0, 1 by R? If I had a linear functional on CR, would we have the same conclusion? What if we had Rn? Instead of R, we went to Rn, and maybe to some more general topological spaces. Okay, and the answer is yes, this can be extended, and it leads to a very powerful Res, and the correct name would, I think, be Res Kakutani theorem, representation theorem. So I will write it first, the statement. There will be many ingredients in the statement itself, which you will need me to define for you. Some of you will know that, of course. Okay, so let me state this for general. So here we go. So let X be, and if you don't understand many of these terms, don't worry, we'll come back to them. So X is a locally compact Hausdorff space, topological space, and delta is a positive linear functional. Okay, so what is CCX? So this is all continuous functions on X with compact support. I will make this very clear, but this is just like C01, but now I have a locally compact topological space here. And to make sense of things, then I need the CCX. So we'll see this in more detail, okay? Then there exists a sigma algebra M in X, which contains all Borel sets of X, and B, a unique positive measure mu on M, such that delta of F is represented as an integral with respect to mu for every F belonging to CCX, and mu has some nice properties. Okay, I will make this nice properties very precise in what follows after I have told you what exactly the terms here mean. These properties are basically completeness and some type of regularity and finiteness. Okay. So when we start proving these, I will state, maybe I should state it here. Okay, let me do it so that at least you have seen this. The first thing is so for compact sets, the measure is finite. Okay, for every, this is part of the regularity condition. So for every measurable set E, mu, the measure of E is the inf of sets, measures of open sets in which E lies, which contain E. Okay, I am going to continue to the next page. I'm going to stop sharing this and start with the next one, okay? Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Okay. So the third condition is so the measure of E is also equal to the supremum of all compact sets contained in E for every open E. So that's why 2 and 3 I can right now just call almost regularity. It's not completely, but you'll see. And for every E in M is finite. And this last condition you should recognize. What is it? Please tell me. What does this mean? What is fourth condition called? You spent some time doing this. This is?
Mu is complete.
Mu is simply complete. Okay. So let's go back now to the statement. What did we have? We had a locally compact Hausdorff space. And then we had this, we replaced C01 by CCX. Okay. So X is a locally compact Hausdorff space. Now, you know, C01 closed interval is a compact space and it's Hausdorff. We know that, okay? So what do I mean by a locally compact Hausdorff space? And then we have CCX. So what is CCX? Let's just go over these things for a bit. So some so let's just recall these. So if X is a When is X Hausdorff?
When two distinct points can be separated by two disjoint open
Okay.
sets which contains this point like ux and
Okay,
uy.
so let me just make this, yeah, right. So let me just make this thing that if I do not say open neighborhood, it still means an open set. So I will call for any P belonging to X by a neighborhood V of P, we shall mean V an open set. Okay, so neighborhoods will be open for us. Okay, so this. So the neighborhood itself is also, when I say neighborhood, we need to understand that it's open. And X is Hausdorff. I think I can skip. All of you would know that. Okay, I might as well give you, what is it? So if you take X, Y belonging to X, X not equal to Y, there exists U, V neighborhoods of X and Y respectively, right?
Yes, ma'am.
So locally compact space,
Every point has a compact neighborhood.
if every X belongs to X has a neighborhood. We remember our neighborhoods are just open set, is compact, right? So we have our locally compact Hausdorff space. What are prime examples of locally compact Hausdorff spaces?
R is locally compact.
Rn. Okay. All right. So you with the Euclidean metric. So, in fact, an infinite dimensional Banach space cannot be locally compact. Okay, but okay, we are not worried about that. Then, now so I have my X in place. It's a locally compact Hausdorff space, and it's a topological space. So now I need to make sense of CCX for you. So for that, if F is any function defined on X, we define the support of F written just to be, so you take the sets of all the elements where Fx is not 0 and take its closure. Okay, so that is the support of F. And then so what is the support of the zero function, a function which takes everything to 0?
Empty.
Sorry, that's empty.
Empty.
And the other extreme will be, suppose F takes a non-zero constant value throughout. So what will
It's the
that
whole
support be?
set. It's the whole set.
It will be the whole topological space X, right? So just okay. So this is what, now let me come to the space CCX. What is this? It's the collection of all continuous functions on X with support F a compact set. Okay. So what are the kind of elements in CCX? Maybe if I take X to be R, anything like this. Slope is not right. Such functions will be in CCR. But a function like which is going to not really 0 is not in CCR. Okay. All right, so now we need to give some structure to CCX. And just before we go, if I take, move on, if I take X to be 0, 1, what will CCX be? What do you think? Right?
Yes.
In
Yes,
fact,
sir.
if you take X to be any compact topological space, CCX will be just C of X. Okay. So we have seen this version of a C01. Okay. Now I want to give CCX a vector space structure. Why do you think this is true?
Continuous functions forms vector space.
We need some more condition, right? So you need some. First of all, is this non-empty? Why would CCX be non-empty? Trivially, at least the 0 function is here, isn't it?
Yes.
Yeah, so 0 function, so this is a non-empty set, and we define the usual addition pointwise and scalar multiplication. So what do I need? So continuity is not a problem. So F plus G, alpha F are continuous, of course, if F, G, R and alpha belongs to C. So what about the support? What can you say about support of F plus G? Do you agree with this? If I say support of F plus G must lie in the union of these two supports? At least. I can't say it's equal, but at least it will lie in the union. Yes?
Yes. Yes.
So if this is if these two are compact, the union will be compact, finite union. Okay. So F plus G is in CCX. And what can you say about the support of alpha F?
That is support of.
Sorry, I didn't hear that.
support of F. Okay, if alpha is not equal to 0, otherwise it becomes entirely 0. So now a whole set X, because if alpha is 0, alpha F is 0.
So it will be
It's
empty,
not
no?
equal to 0. Empty, sorry, empty.
So compact. Therefore, alpha F belongs to CCX. So therefore, CCX is a vector space. Okay, before I move on to the next set, just because we are with CCX, suppose I define, suppose this X is my locally compact space and X M mu is a measure space. And somehow we know that mu of K is less than infinity for all K compact. Fine. Now if we define what can you say about this delta? Is it, first of all, is it well defined? Does this integral exist? And if it does, is it going to be linear? If it exists, then I think we can assume it's linear because of all the work we have done in the past few lectures, right? So the main thing is, why should this exist? Is it finite? Can you say? Can anybody tell me? Why should this be finite?
Since F has compact support.
Yes, exactly. F has compact support. So if I write okay, maybe I shouldn't. Okay, I'm assuming I'm jumping a bit, but this is just, this will be support F. Everywhere else this will be, this is equal to, I mean, this is going to be outside support F, its integral is 0. And what is this? Remember, we want to show it's integrable. So what's this going to be? F is on the support of F, it's a continuous function, compact set. So it must be bounded, isn't it?
Okay, it is less than or equal to some M.
Some M, M is a bad number. C and because this is compact and this is part of our hypothesis, this is finite, okay? Because this is so this is compact. And we said that we are assuming this property for mu. So this mu k less than finite k compact is sort of just to show this delta is a linear function. I need such things, okay? So it's a desirable property to have. Okay. So this is a linear function on CCK. Linearity will follow. So this means, of course, I should write this implies f is integrable. Okay. So this is fine. And then in fact, you can also note this is positive. What does it mean to be positive? Recall. For here in this context, let me say a linear functional from here CCX to C is positive if f greater than equal to 0 implies f is greater than equal to 0. And you can see from our definition of delta f, this is going to be positive if f is positive. Okay, we have shown this. Okay. So what the Res Representation Theorem, the general one, we are trying to say is the converse is also true. If so, this delta is a positive linear functional on CCK, and every positive linear functional is also exactly of this form for an appropriate choice of mu and an appropriate choice of this sigma algebra M. Okay, so this is what we are trying to do here. All right. How much time do I have left? About, okay. Can I, today, can I take a little bit more time? Maybe 5 more minutes after?
No, yes, yes.
Is there a lecture afterwards?
No, tutorial only.
Okay. I'll try and finish in time. All right. Now some notation, which is pretty standard. So we will say K, we'll use this notation to mean if the following is true. The following things hold. 1, K is a compact subset of X. 2, F belongs to CCX. Third, F takes values between 0 and 1 only. And finally, F takes the value 1 on K. So all these 4 points are encoded in this notation. Okay, so let's agree to call it K less than F, though one side is a set and the other side is a function. Okay, so I will use this frequently. So, and I'll keep reminding you, of course, but let me set this notation, and similarly, F less than V will mean V is an open subset of X. F belongs to, so now from now, X is a locally compact Hausdorff space. Okay, I will not repeat it. It's all, we always assume that unless otherwise stated. 0 is less than equal to Fx is less than 1. And finally, the support of F sits inside V. Okay, so this F less than V will encode these 4 properties. And if I write we'll see this notation used, K less than F less than V, which will mean both of those, all these 8 conditions, all the above hold. Okay. So I am doing all this by now. This is clear why I wrote CCX. I gave you the vector space structure and I told you about the integral. But from here, this notation onwards, I needed to give you some idea of the proof of this theorem. Okay. And a major theorem that we'll keep using for this proof is the Eurozone's lemma. Some of you would have seen this. I am not going to attempt to prove it here. You can look at Rudin's book. But I will use it. And I hope some of you remember it. It just simply says, if X is a locally compact Hausdorff space, V is open in X and K is subset of V, K compact, then there exists an F belonging to such that K is less than F is less than V. Okay, so this will be one of our key lemmas we will make use of. Have you seen this lemma before? Anybody has seen this?
Yes, ma'am.
Okay, and I will sometimes use this lemma in the conclusion. I will, instead of writing this in this new notation, this is simply saying in terms of characteristic functions, I can write there exists an F belonging to this space compact continuous functions on X such that the characteristic function of K, this function, is less than F is less than the characteristic function of V. Okay, so here is a homework for you. Verify. So this means this is pointwise. Okay, these are functions. So this is the usual meaning of a function being less than the other. And I'm trying when I'm writing this thing between a set and a function to make it a bit curved, but it doesn't always work. So keep that in mind. Okay. And because of Eurozone lemma, we can also show this result on partition of unity. Which again, I will have an occasion to use, and I'm just telling you here. So suppose V1, V2, Vn are open subsets. Can you hear me?
Yes, ma'am. Yes.
K is compact and K is contained in So the union of Vn. So in Eurozone's lemma, you had a single open set V. K was contained in this V. Now we have a union of open sets, which is still open. So now V can be written like this. And the conclusion is then there exists functions H1, H2, Hn. Maybe I should write it like this. Hi is less than Vi. Okay. So this means all those four things I had listed there, such that so the sum is exactly 1 on K. Okay, so this is why it's called a partition. So you have these functions H1, H2, Hn. So that's why this is called a partition of unity. Okay. So there might be some more results which I will remind you of in our attempt to see a proof of the Res representation theorem. Okay. So I'm just going back to the statement. Oh, I don't have it here. Oh, I do have it here. So today is some problem with my internet, I think. I apologize for this. Okay, so hopefully I've got everything in place. And this is a long proof. I won't say it's a difficult proof, but it has many parts to prove. And you see, so what do I have to prove for the Res representation theorem? I have to prove the existence of a sigma algebra M. I have to show that there is a mu defined on M. And then we have to verify all the properties. So the two regularity-like properties, completeness, and then show that M contains the Borel sets. Okay, so those are the essential parts of that proof. And of course, show that the functional I'm talking about can be represented in terms of the integral. So this condition holds on. So that's the main thing. You have linear functional positive. Then there exists M and mu such that this happens, and then mu does all those 4 or 5 conditions I wrote down. So the first thing then I have to do is, and of course, uniqueness. Let's not forget uniqueness. Maybe that is the easier thing to prove. So I should do that. So let's see. Let me try proving how much time do I have, Dr. Reddy? Hello.
Sorry, yeah, actually, so time is only 1 minute is left, but you can take 5 more minutes if you want.
Okay. So let me try just prove the uniqueness part. So suppose there exists measures mu1, mu2. So mu is unique. Okay, the sigma algebra we construct. Suppose M and mu1, mu2 are measures satisfying. What are the conditions? So And then what else did we have there? The finiteness property, then the regularity properties, so I want you to want that I write this again and again so that we get this in our minds. So the sup over compact sets K contained in E, K compact for some E's are open, and finally complete. Mu i's are complete. In the way we had defined completeness. Okay, so suppose we have mu1 and mu2 doing this. So because of 3, it is enough to show mu 1k is mu 2k for all compact sets. So you fix k belonging to M and you fix an epsilon greater than 0. Okay, compact. Okay, now we know from 1 that mu 2k must be finite. And mu 2k is defined as inf of mu 2 of V such that V is open okay. So therefore, there exists open V such that mu 2V is less than, because it's no longer the right. So now I have K, a compact set K contained in an open set V. So by our Eurozone's lemma, there exists an F in this such that, and I will write it in terms of the characteristic functions. Okay, now what do we have? Therefore, mu 1k and these are the properties of the integral we know very well now. But this is nothing but the linear functional at f. But that's also equal to the integral with respect to d mu 2. And that's less than equal to and that is simply mu 2v, and that we have shown is less than the top of page 17 there. Okay, so what do we have? Now, epsilon was arbitrary, of course, so this means, and then similarly, starting with mu1, similarly, you can show the reverse, just interchanging the roles of mu1 and mu2. And this will give you, okay. Okay, I will stop here. I will revisit this because I think I've been a bit quick proving this. And let's stop here now.